Right now, 400 billion stars burn inside our galaxy alone. At least 1 in 4 of them hosts a rocky planet in the zone where liquid water could exist. The universe has been running this experiment for nearly 14 billion years, across 2 trillion galaxies, on a number of worlds so large it exceeds the grains of sand on every beach on Earth. The math says the cosmos should be teeming with intelligence. It says we should have detected a signal, intercepted a probe, or stumbled across the unmistakable fingerprint of engineering on a cosmic scale by now. We have found nothing. Absolute silence. And the reason that silence exists may be the most terrifying discovery science has ever made about the future of every civilization, including ours. If you enjoy journeys that challenge how you see our place in the universe, go ahead and hit that like button and subscribe. It genuinely helps this channel keep exploring the biggest questions out there. Now, with all that said, settle in and get comfortable. Let's begin. Start counting. 1 star per second. Do not stop. Do not sleep. Do not eat. Just count. 1, 2, 3. At that pace, it would take you roughly 12,600 years to count every star in the Milky Way galaxy. You would begin counting before the construction of the Great Pyramid at Giza, and you would still be counting today, with billions left to go. Our galaxy contains approximately 400 billion stars. Each one is a furnace of nuclear fusion, burning hydrogen into helium, flooding space with light and energy. Many of them have been burning for billions of years. Some ignited before the Earth even existed. And the Milky Way is not special. It is one galaxy among approximately 2 trillion in the observable universe. 2 trillion galaxies, each containing billions or hundreds of billions of stars, are scattered across a volume of space 93 billion light-years in diameter. Multiply it out and you reach a number so large it loses all human meaning. There are more stars in the observable universe than there are grains of sand on every beach, every desert, and every ocean floor on Earth. Somewhere around 10 to the 24th power individual suns are burning right now, at this very moment, as you listen to these words. That number alone should make you pause. But what transforms it from merely staggering into genuinely unsettling is what we have learned about those stars over the past 3 decades. Because stars, it turns out, almost always come with planets. Before 1995, humanity had never confirmed the existence of a single planet outside our solar system. We assumed they were out there. The physics of star formation strongly suggested that rotating disks of gas and dust around young stars would coalesce into planetary bodies. But assumption is not evidence. We had 0 confirmed exoplanets. Then, in October of 1995, Michel Mayor and Didier Queloz announced the detection of 51 Pegasi b, a gas giant orbiting a sun-like star 50 light-years away. That single discovery cracked open a door that has never closed. Within a decade, hundreds of exoplanets had been confirmed. Then came the Kepler Space Telescope, launched by NASA in 2009. Kepler stared at a single patch of sky in the constellation Cygnus for 4 years, monitoring the brightness of over 150,000 stars simultaneously. It was looking for transits, the tiny dip in starlight that occurs when a planet passes in front of its host star, as seen from our vantage point. The results were revolutionary. Kepler alone confirmed more than 2,700 exoplanets and identified thousands more candidates. But the real significance was statistical. By analysing how many planets Kepler found in its small field of view, astronomers could extrapolate to the entire galaxy. The conclusion was stunning. Planets are not rare. Planets are everywhere. The data showed that virtually every star in the Milky Way has at least one planet orbiting it. Many stars have multiple planets. Planetary systems are the rule of the cosmos, not the exception. When you look up at the night sky, there are actually more unseen planets out there than there are visible stars. But Kepler revealed something even more specific and far more provocative. Among all those billions of planets, a significant fraction sit in what astronomers call the habitable zone. This is the orbital region around a star where temperatures allow liquid water to exist on a rocky planet's surface. Not too close, where water boils away. Not too far, where it freezes solid. The habitable zone is the sweet spot, the range of distances where the basic chemistry of life as we understand it becomes possible. Analysis of Kepler data, combined with follow-up ground-based surveys, produced a number that changed the conversation entirely. At least 1 in 4 Sun-like stars hosts a rocky planet in the habitable zone. Some estimates push that figure higher, but even the conservative floor is extraordinary. 1 in 4. In a galaxy with roughly 400 billion stars, that means there are billions of potentially habitable rocky worlds in the Milky Way alone. Not across the entire universe, just in our galaxy. Just in our neighborhood. Billions of worlds where the temperature is right, where liquid water could pool on the surface, where the fundamental ingredients of biology could theoretically come together. Now add time. The universe is approximately 13.8 billion years old. The Milky Way is nearly as ancient. Our Sun and solar system formed about 4.5 billion years ago, but many stars in our galaxy are far older. Some have been burning steadily for 10 or 11 billion years. Their planets have existed for twice as long as Earth. Any life that arose on those ancient worlds had a head start measured not in thousands or millions of years, but in billions. Let that head start become concrete for a moment. Our solar system formed approximately 4.6 billion years ago from a cloud of gas and dust enriched by the deaths of earlier stars. But the Milky Way was already ancient by then. Stars had been forming in this galaxy for roughly 9 billion years before our Sun ignited. That means there are star systems in the Milky Way that are 5, 6, or even 7 billion years older than ours. Planets orbiting those stars had finished cooling, developing oceans, and cycling through their early chemistry while the material that would eventually become Earth was still drifting as uncoalesced debris in a stellar nursery. If life arose on any of those older worlds at roughly the same pace it arose on Earth, emerging within a few 100 million years of stable conditions, then biology could have been thriving on those planets for 10 billion years. That is more than twice as long as life has existed on Earth, more than twice the time to evolve complexity, develop intelligence, and build technology. To put the timescale in perspective, consider what happened on Earth in the last 500 million years alone. 500 million years ago, the most complex organisms on the planet were soft-bodied creatures drifting in shallow seas. In that span, life produced fish, then amphibians, then reptiles, then mammals, then primates, then a species that split the atom and walked on the moon. 500 million years. Now imagine a planet that had not 500 million years but 5 billion, 10 times longer. A civilization arising on such a world could have reached our current level of technology billions of years ago. Billions. They could have had a technological head start so vast that our entire recorded history would not register as a rounding error on their timeline. The universe has been running this experiment on an almost incomprehensible number of worlds for an almost incomprehensible amount of time. The raw ingredients are abundant. The opportunities are staggering. The timescales are immense. Under these conditions, the emergence of intelligent life seems not just plausible, but practically inevitable. Not on every world, of course, not even on most worlds, but on some fraction, however small, of those billions upon billions of habitable planets orbiting billions upon billions of stars across billions of years of cosmic history. Intelligence should have arisen. This is the foundation of a question that has haunted science for over 70 years. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at the Los Alamos National Laboratory in New Mexico. The conversation drifted toward flying saucers, a popular topic at the time, and then toward the broader question of extraterrestrial life. Fermi, one of the most brilliant physicists of the 20th century and the architect of the first nuclear reactor, did some quick mental arithmetic. He considered the age of the galaxy, the number of stars, the likelihood of planets, and the time it would take a civilization with even modest spacefaring technology to colonize the galaxy. His conclusion came in the form of a deceptively simple question that has echoed through every decade of scientific inquiry since. Where is everybody? The question sounds casual. It is anything but. Fermi had realized something deeply troubling. Even if you assume that interstellar travel is slow, limited to a small fraction of the speed of light, and even if you assume that civilizations expand only gradually, establishing a new colony every few thousand years, the math still works out to a startling conclusion. A single civilization arising anywhere in the Milky Way at any point in the last several billion years could have colonized the entire galaxy in roughly 50 to 100 million years. That sounds like a long time, but it is less than 1% of the galaxy's age. The galaxy has had enough time for this to happen, not once but hundreds of times over, thousands of times over. Yet when we look up at the sky, we see no evidence that it has ever happened. No signals, no probes, no megastructures, no unexplained alterations to stellar systems, no artifacts in our solar system, nothing. This is the Fermi Paradox, and it is not just a puzzle, it is a crisis of expectation versus observation, one of the deepest unresolved problems in all of science. To understand why the paradox cuts so deep, you need to appreciate what kinds of evidence we should expect to find if advanced civilizations existed or had ever existed anywhere in our galaxy. The first and most obvious category is electromagnetic signals. Since the late 1950s, scientists involved in the search for extraterrestrial intelligence, known as SETI, have been scanning the sky for narrowband radio signals. These are signals confined to a very tight range of frequencies, the kind produced by deliberate technological transmission rather than natural astrophysical processes. A civilization that wanted to announce its presence could broadcast a powerful radio beacon detectable across thousands of light years. Even a civilization that was not deliberately signaling might leak radio emissions from its communications infrastructure, just as Earth has been leaking television broadcasts, radar pulses, and satellite communications into space for over a century. The SETI Institute's Allen Telescope Array in Northern California was designed specifically for this search. Breakthrough Listen, the most ambitious SETI program ever funded, has been using the Green Bank Telescope in West Virginia and other instruments to survey thousands of nearby stars across frequencies from 1 to 12 gigahertz. Machine learning algorithms now sift through millions of candidate signals, filtering out terrestrial interference to hunt for patterns that no natural source could produce. In 2025, a revolutionary artificial intelligence system developed for Breakthrough Listen achieved a 600-fold speed increase in signal processing and reduced false positives by nearly a factor of 10. The technology has never been better. The sensitivity has never been greater. The number of stars surveyed grows every year. The result, after more than 6 decades of searching, is silence. No confirmed extraterrestrial signal has ever been detected, but radio is not the only channel. Advanced civilizations might build structures large enough to be visible across interstellar distances. A Dyson sphere or Dyson swarm, a megastructure designed to capture most or all of a star's energy output, would radically alter the star's observable characteristics. Instead of emitting visible light, a star enclosed in such a structure would glow primarily in infrared, radiating waste heat. Astronomers have conducted searches for exactly this kind of anomalous infrared excess among catalogues of millions of stars. In 2015, the star KIC 8462852, informally known as Tabby's star, briefly excited the scientific community with irregular dimming patterns that defied easy natural explanation. For a moment, a Dyson swarm seemed like a genuine possibility. Subsequent observations determined the dimming was caused by dust, not alien engineering. Every candidate for artificial megastructures has so far been explained by natural phenomena. A civilization might also leave chemical fingerprints in the atmosphere of its home planet. Industrial pollution, certain artificial gases, or the byproducts of large-scale energy production could be detectable through spectroscopic analysis of exoplanet atmospheres. The James Webb Space Telescope, operational since 2022, is now capable of analyzing the atmospheric composition of planets orbiting nearby stars. NASA has established a technosignatures study analysis group, active through 2026, specifically to integrate technosignature searches into its broader exoplanet and astrobiology programs. Researchers are now looking not just for biosignatures, chemical signs of life, but also for technosignatures, chemical or physical signs of technology. Nitrogen dioxide from combustion, chlorofluorocarbons that no natural process can produce, city lights on a planet's night side, solar panels alter a planet's reflective spectrum. The tools to detect these markers are rapidly improving, yet so far, nothing. There is another category of evidence that makes the silence even harder to explain: self-replicating probes. In the late 1940s, mathematician John von Neumann described a theoretical machine capable of building copies of itself from raw materials found in its environment. His work, published posthumously in 1966, laid the foundation for one of the most powerful arguments in the Fermi Paradox. Applied to space exploration, a civilization would need to launch only a single such probe. The probe would travel to a nearby star system, harvest asteroids or other material, construct copies of itself, and send those copies onward to additional star systems. Each new probe would repeat the process. The number of probes would grow exponentially, and within a few tens of millions of years, every star system in the galaxy would contain at least one. The civilization that launched the original probe would not need to be alive to see the result. The probes would continue autonomously, exploring and cataloguing the galaxy long after their creators were gone. The mathematics of this is well established. Even travelling at a modest 1% of the speed of light, self-replicating probes could blanket the Milky Way in under 100 million years. That is less than 1% of the galaxy's age. If any civilization in the last several billion years had developed and deployed such probes, evidence of their presence should be everywhere. In our asteroid belt, on the surfaces of moons, in the cometary clouds surrounding our solar system, we have found nothing. In 2025, a remarkable opportunity arose to test this idea in real time. On July 1st of that year, astronomers discovered the third known interstellar object to pass through our solar system, designated 3I, Atlas. Like its predecessors, the interstellar object Oumuamua in 2017 and comet Borisov in 2019, this body originated from another star system and was merely passing through. Breakthrough Listen immediately turned multiple telescope arrays toward the object. The Allen Telescope Array observed it across frequencies from 1 to 9 GHz. The Meerkat Array in South Africa searched for radio emissions down to a sensitivity equivalent to the power output of a mobile phone. The Green Bank Telescope, the largest steerable single-dish radio telescope on Earth, observed the object less than 24 hours before its closest approach, achieving sensitivity to transmitters producing as little as 1/10 of a watt. No artificial signals were detected from 3I, Atlas. At any frequency, the object behaved exactly as a natural comet would. Another opportunity, another silence. Consider what this means when you pull it all together. We live in a galaxy containing hundreds of billions of stars. A significant fraction of hosts have rocky planets in habitable zones. The galaxy is old enough for civilizations to have arisen billions of years before us. Even with conservative technology, a single civilization could have explored or colonized the entire Milky Way many times over. We have searched for radio signals, optical signals, infrared anomalies, atmospheric technosignatures, and physical probes. We have examined interstellar visitors that pass through our own solar system. Every search has returned the same answer: nothing. And here is where the numbers become not just surprising, but genuinely alarming. In 1961, astronomer Frank Drake wrote down an equation to estimate the number of detectable civilizations in the Milky Way. The Drake equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction of those planets where life develops, the fraction where intelligence evolves, the fraction that develop detectable technology, and the average lifetime of such technological civilizations. When Drake first proposed the equation, almost every factor was unknown. Today, thanks to Kepler, the James Webb Space Telescope, and decades of astrophysical research, the first three factors are reasonably well constrained. Stars form at a rate of roughly 1 to 3 per year in our galaxy. Nearly every star has planets. At least 1 in 4 Sun-like stars has a rocky world in the habitable zone. These numbers are not guesses. They are observational results derived from data. The remaining factors, the biological and sociological unknowns, are where the uncertainty lies. What fraction of habitable planets actually develop life? Nobody knows. We have exactly one data point: Earth. What fraction of living worlds produce intelligence? Again, one data point. What fraction of intelligent species develop technology capable of producing detectable signals? One data point. And how long do such civilizations last? We do not even have a complete data point for that, because our own technological civilization is still in its infancy. But here is the critical observation. Even if you assign deeply pessimistic values to the unknown factors, even if you assume that life arises on only 1 in a million habitable worlds, that intelligence evolves on only 1 in a million of those, and that technology emerges on only 1 in a million of those, the sheer number of opportunities is so enormous that the expected number of civilizations still comes out to a number much greater than 0. You have to push the probabilities to absurdly low levels, probabilities so small they start to strain credibility, before you get an equation that predicts we should be alone. In 2016, astrophysicists Adam Frank and Woodruff Sullivan approached the problem from the opposite direction. Instead of trying to estimate how many civilizations exist now, they calculated how pessimistic you would need to be for humanity to be the only technological species in the entire history of the observable universe. Their answer: the probability of a civilization arising on any given habitable planet would need to be less than 1 in 10 billion trillion. That is 1 in 10 to the 22nd power. For the Milky Way alone, the odds of us being unique require the probability to be less than 1 in 60 billion. These are extraordinarily tiny numbers. Given what we now know about the abundance of habitable worlds, most scientists find it very difficult to believe that the actual probability is that low. A 2024 study by planetary scientists Alan Stern and Taras Geria attempted to refine the equation further. They argued that 2 factors previously overlooked dramatically reduce the number of worlds where intelligence can arise: the requirement for a planet to have both significant oceans and continents in the right proportion, and the requirement for long-lived plate tectonics lasting at least 500 million years. Both conditions are necessary for the kind of complex chemical cycling that sustains a biosphere capable of producing intelligent life. Both conditions may be exceptionally rare. When they folded these new terms into the Drake equation, the probability of a habitable planet producing a communicative civilization dropped to between 0.003% and 0.002%. This is far lower than the optimistic 100% that some earlier estimates assumed. But even at these reduced probabilities, applied across hundreds of billions of habitable worlds, the expected number of civilizations in the Milky Way is not 0. It may be small. It may be in the tens or hundreds rather than millions, but it is not 0, and yet the sky is silent. In 2025, a Nature Astronomy survey polled over 1,000 scientists working in relevant fields. 87% agreed that at least basic extraterrestrial life exists somewhere in the universe. More than 67% agreed that intelligent extraterrestrial life is out there. This is not fringe speculation. This is the mainstream scientific consensus. The ingredients exist. The time has been sufficient. The opportunities are vast. The expectation among the people who study these questions professionally is that we are not alone, but expectation is not evidence, and the gap between what we expect and what we observe is not narrowing, it is widening. Every year, our detection capabilities improve. Every year, we survey more stars, analyze more atmospheres, and process more data. And every year, the silence deepens. The Breakthrough Listen initiative has searched thousands of nearby stars with instruments sensitive enough to detect transmitters far less powerful than Earth's own military radar. Nothing. NASA's technosignatures program is systematically integrating alien technology searches into its exoplanet science portfolio. Nothing yet. Deep learning algorithms scan millions of candidate signals and reject them all as terrestrial interference or natural phenomena. The silence is not proof that we are alone. Absence of evidence is not the same as evidence of absence. It is entirely possible that life is out there but has not yet been detected because our instruments are not sensitive enough, because we are looking at the wrong frequencies, because we are searching in the wrong places, or because alien technology takes forms we have not imagined. All of these are valid possibilities, and no serious scientist dismisses them. But there is another possibility, one that is harder to dismiss with each passing year of null results. The silence might not be a failure of detection. It might be data, real, meaningful data telling us something profound about the nature of intelligence in this universe. Think about what the silence requires. It is not enough for one civilization to fail. For the galaxy to be this quiet, given its age and the number of opportunities, essentially every civilization that has ever arisen must have failed to become permanently visible. Every single one. Across billions of years and billions of potentially habitable worlds, not one has built structures we can detect. Not one has colonized widely enough for us to notice. Not one has transmitted signals that have reached us. Whatever is preventing the cosmos from being filled with the evidence of intelligence, it must be something that operates universally. Something that applies not just to one unlucky species on one unlucky world, but to civilizations in general. Something systematic. This is what makes the Fermi Paradox so much more than an interesting thought experiment. It is pointing at a pattern written in silence across a galaxy that should, by every calculation we can perform, be anything but quiet. The stars are there, the planets are there, the chemistry is there, the time is there. Everything needed for the universe to be loud and alive with intelligence has been in place for billions of years, and yet when we listen, there is nothing. Something is stopping civilizations from filling the galaxy. Something is filtering them out before they can become visible on cosmic timescales. The question that matters more than any other in this entire story is a simple one, and the answer to it may determine the future of every intelligent species that has ever existed or ever will exist. Where in the journey from dead matter to galaxy-spanning civilization does the filter strike? Has humanity already passed through it, or is it still waiting for us ahead? The easiest response to the Fermi Paradox is also the most tempting. Space is big. Really, really big. The nearest star system to our own, Alpha Centauri, lies 4.3 light-years away. That translates to roughly 25 trillion miles. If you launch the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reached speeds of approximately 430,000 miles per hour during its close passes of the Sun, it would still take that probe over 6,000 years to reach Alpha Centauri. And Alpha Centauri is next door. The average distance between stars in our region of the galaxy is larger still. Cross the entire Milky Way, and you are talking about 100,000 light-years, a distance so vast that light leaving one edge today will not reach the other side until humanity, if it still exists, is unrecognizable from what it is now, so the instinctive answer writes itself. Of course, we have not heard from anyone. The universe is simply too large for signals to reach us. Civilizations might be out there by the millions, happily broadcasting into the void. but their transmissions are either too faint by the time they cross those immense distances, aimed in the wrong direction, or still en route, creeping toward us at light speed across a gulf measured in millennia. This is the distance explanation. It feels reasonable, it feels comforting, and it is almost certainly not sufficient. Here is why. The distance argument treats civilizations as stationary. It imagines alien societies sitting quietly on their home planets, sending out radio whispers and waiting for a reply. But civilizations do not have to stay put. They can move, they can build, they can expand. And even with technology only modestly more advanced than what humanity possesses right now, expansion through the galaxy is not just theoretically possible. It is, given enough time, practically inevitable. Consider the math. A civilization capable of building generation ships, large spacecraft designed to sustain populations across centuries of travel, could send colonists to a nearby star system within a few hundred or a few thousand years. Once established, that colony could build its own ships and send settlers to the next system. Each new colony repeats the process. The expansion is not fast by human standards. Perhaps one new system colonized every 1,000 years, perhaps every 10,000 years. The exact speed does not matter much because the galaxy provides an enormous amount of time. Even at the most conservative pace imaginable, a civilization expanding at 1% of the speed of light and pausing for 1,000 years at each new system to build up its colony would saturate the Milky Way in a time frame that barely registers on the galactic clock. The colonization math, as we established, is not the bottleneck. Time is abundant. Opportunity is abundant. The bottleneck is something else entirely. The Milky Way has existed for roughly 10 billion years. There has been enough time for this kind of expansion to have occurred 100 times over, sequentially, with billions of years to spare between each wave. And colonization ships are not even the most efficient option. Self-replicating probes, the von Neumann machines, could accomplish the same thing faster and without risking a single living being. A probe arrives at a star system, mines local asteroids for raw material, constructs several copies of itself, and launches those copies toward neighboring stars. The probe does not need to sustain a living crew. It does not need breathable air, food, or gravity. It just needs raw material and a set of instructions. The exponential growth of such a swarm means that the entire Milky Way could be saturated with autonomous machines in a time frame that is trivially short compared to the galaxy's age. The launching civilization could go extinct the day after deploying the first probe, and it would not matter. The swarm would continue. It would fill the galaxy regardless. This is what makes the distance argument collapse. Yes, space is vast. Yes, individual signals weaken over interstellar distances. But civilizations are not limited to signals. They can physically expand. They can send machines that replicate. And the timescales required for galactic-scale expansion are trivially short compared to the time the galaxy has been available. If even one civilization, anywhere in the Milky Way, at any point in the last several billion years, had begun this process, evidence of it should be everywhere. In our solar system, in the spectral signatures of nearby stars, in the infrared glow of stellar engineering, everywhere. The distance between stars is not a wall, it is a speed bump. Given enough time, even a speed bump is meaningless. And the universe has given plenty of time. So we cannot simply wave away the silence by pointing at a map and saying the distances are too great. We need a deeper answer. We need to consider the possibility that the silence is not a failure of communication or detection. It might be a failure of existence. Civilizations might not be out there in the numbers we expect, or they might not last long enough to make themselves known. And the framework for thinking about this possibility has a name that carries more weight with each passing year of null results. In 1996, economist and futurist Robin Hanson published an essay titled "The Great Filter, Are We Almost Past It?" The paper introduced a concept that has since become central to discussions about the Fermi Paradox. Hanson's argument was straightforward. Between the formation of a habitable planet and the emergence of a galaxy-spanning civilization, there is a long chain of necessary steps. A planet must form in the right conditions. Chemistry must give rise to biology. Simple life must evolve into complex life. Complex life must develop intelligence. Intelligence must produce technology. Technological civilization must survive long enough to expand beyond its home world. Each of these steps has some probability of occurring, and the product of all those probabilities determines how many civilizations reach the final stage. The Fermi Paradox tells us that the product of all those probabilities is extremely low. The galaxy is not filled with visible civilizations. This means that somewhere along the chain, at least one step must be extraordinarily improbable. Hansen called this the Great Filter. It is the bottleneck, the barrier, the point where the overwhelming majority of potential civilizations are eliminated. The critical question, the one that determines whether the Great Filter is a source of comfort or a source of terror, is its location. Is the filter behind us, meaning humanity has already passed through the hardest step? Or is it ahead of us, meaning the hardest step is something we have not yet faced, and that most civilizations that reach our stage of development do not survive what comes next? Let us walk through the chain and examine where the filter might sit. The first candidate is the origin of life itself, a process called abiogenesis. Life on Earth arose surprisingly early. The planet formed approximately 4.5 billion years ago. The heaviest period of asteroid bombardment tapered off around 3.8 billion years ago, and the earliest evidence of microbial life dates to roughly 3.7 billion years ago, possibly earlier. Life appeared on Earth almost as soon as conditions allowed it. This suggests that abiogenesis might be relatively easy, that given the right chemistry and environment, the transition from non-living matter to self-replicating molecules happens readily. If that is true, then the origin of life is probably not the Great Filter. It would mean that microbial life is common across the galaxy, perhaps even ubiquitous on habitable worlds. But we must be cautious. We have exactly one example of abiogenesis, and it happened on our planet. We cannot yet determine whether life arose easily here because the process is genuinely straightforward, or whether Earth happened to win an incredibly unlikely chemical lottery. Some biochemists argue that the specific sequence of events required to build a self-replicating RNA molecule from simple precursors is so improbable that it might happen on fewer than 1 in a billion habitable worlds. Others argue that multiple chemical pathways could lead to life, making it far more likely. The honest answer is that we do not know. Abiogenesis remains a candidate for the Great Filter, but the speed with which life appeared on Earth weakens the case. The second candidate is the leap from simple to complex life. For roughly 2 billion years after life appeared on Earth, nothing much happened. The planet was dominated by single-celled prokaryotes, organisms without a nucleus or internal membrane-bound structures. Then, approximately 2 billion years ago, something extraordinary occurred. One prokaryotic cell engulfed another, and instead of digesting it, the two cells formed a symbiotic partnership. The engulfed cell became the mitochondrion, the energy-producing powerhouse found in virtually every complex cell on Earth. This event, called endosymbiosis, gave rise to eukaryotic cells, the type of cell that makes up every animal, plant, fungus, and protist alive today. Without this single event, complex multicellular life as we know it could never have evolved. The critical detail is that this appears to have happened only once in the entire history of life on Earth. In 2 billion years of microbial evolution, with countless trillions of cells interacting in every conceivable environment, the specific merger that produced eukaryotic cells occurred exactly one time. This suggests that the transition from simple to complex cellular life might be genuinely improbable. If it took 2 billion years and trillions of interactions to happen once on a planet teeming with microbes, perhaps on most living worlds it never happens at all. This is a strong candidate for the Great Filter, a universe full of bacteria-covered planets but almost devoid of anything more complex. The third candidate is the development of multicellular life. Even after eukaryotic cells arose, It took another billion years or more for organisms to figure out how to cooperate as multicellular bodies. The jump from a single complex cell to a coordinated organism of trillions of cells is not trivial. It requires mechanisms for cell communication, differentiation, and cooperative behavior. It requires suppressing the natural tendency of cells to compete with one another, a tendency that still reasserts itself in the form of cancer. Multicellularity evolved independently multiple times on Earth, which suggests it may not be the primary bottleneck. But the long delay between the first eukaryotes and the first true animals hints that it is not effortless either. The fourth candidate is the evolution of intelligence itself. Life has existed on Earth for nearly 4 billion years. Complex multicellular animals have existed for roughly 600 million years. In all that time, across millions of species, human-level intelligence has evolved exactly once. Dolphins are clever. Octopuses solve puzzles. Crows use tools. But no other lineage on this planet has developed language, mathematics, or technology. The path from animal intelligence to the kind of recursive, symbolic thinking that builds civilizations appears to be vanishingly narrow. Evolution does not aim toward intelligence. It selects for whatever works in a given environment, and brute strength, speed, camouflage, or sheer reproductive output often work better than big brains. Intelligence is metabolically expensive. A human brain consumes roughly 20% of the body's energy, despite representing only 2% of its mass. Most species cannot afford that cost. Those that evolve large brains often do so for reasons unrelated to technology, social bonding, predator avoidance, or foraging efficiency, none of which necessarily leads to building radio telescopes. The fifth candidate involves the planetary conditions required for intelligence to arise at all. This is where the rare Earth hypothesis enters the picture, and where recent research has sharpened the argument considerably. In 2024, planetary scientists Alan Stern and Taras Geria proposed adding two new terms to the Drake equation. The first captures the fraction of habitable planets that possess the right balance of continents and oceans. Too much water, and you get a world entirely covered by deep ocean, with no exposed land for complex surface chemistry. Too little water, and you get a desert world with no oceans to drive the chemical cycling necessary for a rich biosphere. Earth sits in a narrow sweet spot. Stern and Geria estimated that the fraction of habitable planets with this balance might be as low as 0.02%. Their second new term captures the fraction of those planets that sustain plate tectonics for at least 500 million years. Plate tectonics is not just a geological curiosity. It is the engine that drives the carbon cycle, regulates atmospheric composition, recycles nutrients, and maintains the long-term climatic stability that complex life requires. Without plate tectonics, a planet's atmosphere tends to drift toward uninhabitable extremes, either a runaway greenhouse like Venus or a frozen wasteland. Earth has maintained active plate tectonics for billions of years, but this may depend on a specific set of conditions, including planetary mass, internal heat, water content, and the presence of a large moon to stabilize axial tilt. Stern and Geria estimated that the fraction of otherwise habitable planets with long-lived plate tectonics is less than 17%. When you multiply these new factors together, the probability that a habitable planet produces conditions suitable for intelligent life drops to somewhere between 0.003% and 0.002%. This is a dramatic reduction from the optimistic assumption that every habitable planet is a candidate. It means that even among the billions of rocky worlds in habitable zones across the galaxy, only a tiny fraction may have the right geological and hydrological conditions for civilizations to emerge. The rare Earth argument places much of the great filter in the past, in the extraordinary chain of planetary, chemical, biological, and geological conditions that had to align for a species like ours to exist. If this is correct, it is actually good news for humanity. A filter in the past means we have already cleared the hardest hurdle. The reason the galaxy is quiet is not that civilizations arise and then die. It is that civilizations almost never arise in the first place. We are rare. We are lucky. and our future is open. But there is a problem with placing all of the filters in the past. Several problems, in fact. The first problem is that the early steps may not be improbable enough. If abiogenesis is relatively easy, as the speed of life's appearance on Earth suggests, and if the galaxy contains billions of habitable worlds with the right conditions, even a tiny fraction of those worlds producing intelligence still yields a significant number of civilizations. The rare Earth factors reduce the odds, but they may not reduce them to zero. If even a few thousand civilizations have arisen across the Milky Way's history, the question of why none became permanently visible remains unanswered. The second problem is empirical. In February of 2026, astrophysicist Saurabh Rawar published a paper in the monthly notices of the Royal Astronomical Society letters that approached the problem from the opposite direction. Instead of estimating how many civilizations might exist, Rawar asked what the observed silence tells us about how long they can last. His reasoning was elegant. If we assume optimistic values for the biological terms in the Drake equation, meaning that life and intelligence arise on a reasonable fraction of habitable worlds, then the absence of any detected signals imposes a hard upper bound on the average lifespan of technological civilizations. The math is unforgiving. If civilizations are moderately common, the only way to explain the silence is if they are also very short-lived. Under optimistic biological assumptions, the null results from SETI constrain civilizational lifespans to disturbingly brief windows. The more common the intelligence is, the shorter each instance of it must survive to be consistent with the silence. This finding does not prove that the great filter lies ahead, but it demonstrates that a purely past-facing filter is not the only interpretation consistent with the data. If intelligence arises with any reasonable frequency, the observed silence requires that technological civilizations do not persist for long. Something happens to them. Something happens consistently, reliably, and across different planetary systems, different biologies, and different histories. Something universal. The third problem is what we might call the single exception argument. For the silence to be explained entirely by past filters, you need every single factor in the chain to be improbable enough that the cumulative product is essentially zero. But all it takes is one civilization, one time in billions of years, to break through every filter, develop self-replicating technology, and fill the galaxy with evidence of its existence. The past filters would need to be so extreme that not a single world out of billions upon billions, across not a single epoch out of billions of years, ever produced a surviving technological species. That is a very strong claim. And with each exoplanet discovery that reveals yet another potentially habitable world, it becomes harder to maintain. There is a thought experiment that captures this tension vividly. Imagine you are walking through an ancient forest. You know the forest has existed for millions of years. You know the conditions are perfect for birds. You know there are insects for them to eat, trees for them to nest in, and water for them to drink. Everything a bird population needs is present in abundance. And yet as you walk, you hear no bird song. You see no nests. You find no feathers on the ground. One possible explanation is that something about this forest prevents birds from ever existing in the first place. Perhaps the altitude is wrong. Perhaps a specific nutrient is missing from the soil. That is the past filter explanation. Another possible explanation is that birds do appear in this forest regularly, but something keeps killing them before they can establish a permanent population. A predator, a disease, a cyclical catastrophe. That is the future filter explanation. Both explanations account for the silence, but they carry radically different implications for any bird that happens to be alive in the forest right now. If the filter is in the past, the living bird is extraordinary, rare, and possibly safe. If the filter is ahead, the living bird is ordinary, common, and in grave danger. Humanity is that bird. We are alive in the forest. We can hear the silence, and we do not yet know which explanation is correct. What makes the forward-facing filter so difficult to dismiss is that we can already see its outlines in our own history. humanity has existed as a technological civilization for an extraordinarily brief period. If you define technological civilization as the ability to produce detectable electromagnetic signals, we have existed for roughly 120 years. Since Guglielmo Marconi's first radio transmissions in the early 1900s, in that single century, we have developed nuclear weapons capable of ending civilization in an afternoon. We have triggered a planetary climate crisis driven by the same fossil fuel combustion that powers our industrial economy. We have begun developing artificial intelligence systems whose long-term behavior and alignment with human values remain deeply uncertain. Each of these developments represents a plausible extinction mechanism, not in theory, not in science fiction, but in the lived experience of the only technological civilization we know of. And here is the detail that should unsettle you most. These risks are not accidental features of human civilization. They are structural consequences of how intelligence interacts with technology. Any species that discovers nuclear physics will eventually learn to split the atom. Any species that industrializes will eventually alter its planet's atmosphere. Any species that develops computation will eventually build systems more capable than individual minds. These are not human-specific outcomes. They are convergent outcomes of technological development itself. If intelligence arises on 1,000 different worlds through 1,000 different biological pathways, each one will face its own version of the same crossroads. The power to reshape a planet arrives before the wisdom to do it safely. The ability to destroy comes before the ability to endure. A 2024 paper by Michael Garrett, director of the Jodrell Bank Center for Astrophysics, formalized one version of this argument. Garrett proposed that the emergence of artificial superintelligence could act as a great filter, capping the lifespan of technological civilizations at fewer than 200 years. His reasoning was that the development of artificial intelligence, driven by competition within biological civilizations, consistently outpaces the development of multiplanetary capability. By the time a civilization realizes the existential risk, it is already too late. The AI is too advanced, the competition too intense, the institutional safeguards too slow. Garrett noted that on Earth, we are advancing toward artificial superintelligence far more rapidly than we are advancing toward becoming a multiplanetary species. The gap between the two timelines is not closing, it is widening. If Garrett is right, and if this pattern generalizes across civilizations, it provides a clean explanation for the Fermi Paradox. Civilizations arise. They develop technology. Within a few centuries, they either destroy themselves or are transformed beyond recognition by the very tools they created. The window during which they are detectable, broadcasting radio signals into space, building megastructures, or sending out probes, is measured in decades or centuries, not millennia or millions of years. On cosmic timescales, each civilization is a spark, bright for an instant, gone before the light can travel to the nearest neighbor. This reframing changes everything about how we interpret the silence. If the great filter is primarily in the past, the silence is lonely but safe. It means we are among a very small number of civilizations that have ever existed, and our future is open. But if the great filter is primarily ahead, the silence is not empty. It is the accumulated record of every civilization that reached our stage of development and failed to survive what came next. Every quiet star system in the galaxy might represent not the absence of intelligence, but the aftermath of it. Not a void, but a graveyard. And the truly terrifying part is that we cannot yet distinguish between these two interpretations with certainty. The evidence is consistent with both. The past filters are real. Abiogenesis may be difficult. The leap to complex cells may be rare. The geological requirements for intelligence may be stringent. All of this is plausible and supported by evidence. But the forward filter is also real. We can see it taking shape in our own civilization right now. We are living inside the test. We are the experiment in progress. The silence of the universe is not an unanswered question. It is an answer we have not yet learned how to read. It could be telling us that we are miraculous, a fluke of chemistry and geology so unlikely that we may be alone in the cosmos. Or it could be telling us something far darker, that intelligence is not rare at all, that it blooms regularly on worlds across the galaxy, reaching for the stars with the same curiosity and ambition that drives us, and that it consistently, reliably, universally fails to survive its own success. The next question, the one that determines which interpretation is correct, is whether the mechanisms of civilizational failure are truly universal. Whether the forces that threaten humanity right now, nuclear weapons, ecological collapse, artificial intelligence run amok, are isolated accidents of our particular history or inevitable consequences of any species following the technological path. If they are inevitable, then the great filter is not a single barrier, it is a gauntlet. And every civilization that enters it faces the same ruthless odds. There is a window. It opens the moment a species develops the power to reshape its world on a planetary scale. It closes the moment that species either achieves long-term stability across multiple worlds or destroys the conditions that sustain it. That window may be extraordinarily narrow. For humanity, it opened less than a century ago, and the evidence mounting from every direction, from climate science, from nuclear strategy, from artificial intelligence research, from ecology, suggests that the window does not stay open for long. This is the terrifying reason the universe may be so quiet, not because intelligence is rare, not because the distances are too great, not because aliens are hiding or the math is wrong. The universe may be silent because the window between developing world-changing technology and either surviving it or being destroyed by it is so brief that civilizations almost never make it through. They light up, burn bright for a geological instant, and go dark, one after another. Across billions of years and billions of worlds, each one is convinced it is special, each one wrong. To understand why this window might be universally narrow, we need to examine the specific mechanisms that threaten technological civilizations, not as abstract possibilities, but as structural features of how intelligence interacts with power. These are not uniquely human problems. They are problems that any species walking the technological path would almost certainly encounter, because they arise not from the peculiarities of human psychology, but from the physics, chemistry, and game theory of what technology actually does. The first mechanism is the weaponization of fundamental physics. On July 16, 1945, at 5:29 in the morning, the sky above the Jornada del Muerto desert in New Mexico turned white. The Trinity test, the first detonation of a nuclear weapon, released energy equivalent to roughly 21,000 tons of TNT from a sphere of plutonium smaller than a soccer ball. In that instant, humanity crossed a threshold that can never be uncrossed. We discovered that the binding energy of atomic nuclei, the force that holds matter together at its most fundamental level, could be unlocked and directed as a weapon. Within 4 years, the Soviet Union had its own bomb. Within 2 decades, global nuclear arsenals contained enough destructive power to end civilization several times over. Consider what this means in the context of the Fermi Paradox. Nuclear physics is not a human invention. It is a feature of the universe. The strong nuclear force operates identically on every world, orbiting every star in every galaxy. Any species that develops a sufficiently advanced understanding of matter will eventually discover nuclear fission and fusion. The knowledge itself is not optional. It follows directly from understanding the structure of atoms. And once you understand how to release nuclear energy, you understand how to build a nuclear weapon. The path from theoretical physics to existential threat is not a detour, it is the main road. On Earth, this knowledge arrived in a civilization that was already organized into competing nation-states with long histories of warfare. The result was a nuclear arms race that, at its peak in the mid-1980s, produced a combined global arsenal of roughly 70,000 warheads. We came closer to using those weapons than most people realize. During the Cuban Missile Crisis of 1962, Soviet submarine officer Vasily Arkhipov personally prevented the launch of a nuclear torpedo during a confrontation with American naval forces. He was one of 3 officers required to authorize the launch. The other 2 had already agreed. A single individual's refusal may have prevented a full-scale nuclear exchange. In 1983, Soviet Lieutenant Colonel Stanislav Petrov was monitoring the early warning satellite system when it reported that the United States had launched an intercontinental ballistic missile toward the Soviet Union. Minutes later, 4 more launches appeared on screen. Standard protocol required him to report the attack up the chain of command, which could have triggered a retaliatory strike. Petrov judged the alerts to be a system malfunction and reported a false alarm. He was correct. A rare alignment of sunlight on high-altitude clouds had confused the satellite sensors into registering missile launches that did not exist. The world's survival that day hinged on one man's gut feeling overriding his instrumentation. These are not isolated incidents. Declassified records reveal dozens of close calls during the Cold War, moments when miscommunication, technical failure, or political miscalculation nearly triggered a nuclear exchange. And these risks have not disappeared. 9 nations currently possess nuclear weapons. Several of them are locked in active geopolitical rivalries. 2,000. The global arsenal, while reduced from its Cold War peak, still contains an estimated 12,200 warheads as of recent counts, more than enough to devastate global civilization. The risk of accidental or intentional use persists, compounded by the development of hypersonic delivery systems, cyber warfare capabilities that could compromise command and control infrastructure, and the erosion of arms control treaties. Now extrapolate this scenario to any civilization, anywhere. A species develops physics. Physics reveals nuclear energy. Nuclear energy is weaponized. Competing factions within the civilization stockpile weapons capable of ending their world. Survival then depends on maintaining perfect restraint, perfect communication, perfect rationality, across every faction, for every year, for centuries or millennia. A single failure at any point in that chain is extinction. The math is brutal. Even if the annual probability of nuclear catastrophe is very small, say 1% per year, the cumulative probability over a century approaches 63%. Over 500 years, it approaches 99.3%. Given enough time, even unlikely events become near certainties. A civilization relying on nuclear restraint to survive indefinitely is playing a game it will almost certainly eventually lose. The second mechanism is ecological self-destruction. Every technological civilization requires energy. On Earth, the dominant energy source for the past 2 centuries has been the combustion of fossil fuels, coal, oil, and natural gas. These fuels are stored sunlight, captured by ancient organisms and compressed over millions of years into dense reservoirs of chemical energy. Burning them releases that energy along with carbon dioxide, a greenhouse gas that traps heat in the atmosphere. The result is planetary warming. Since the beginning of industrialization, Earth's average surface temperature has risen by approximately 1.4 degrees Celsius. This sounds small. It is not. It has already triggered measurable increases in sea level, shifts in precipitation patterns, intensification of extreme weather events, loss of polar ice, ocean acidification, and the beginnings of ecosystem collapse across multiple biomes. But here is the deeper structural point. The connection between energy use and environmental disruption is not accidental. It is thermodynamic. Any civilization that harnesses large amounts of energy will generate waste heat and waste products. On a planet with a finite atmosphere and finite capacity to absorb waste, energy-intensive civilization will eventually alter the environment that sustains it. The specific form of the disruption depends on the energy source. Fossil fuels produce greenhouse gases. Nuclear energy produces radioactive waste. Even renewable sources, if deployed at sufficient scale, can alter local ecosystems and require vast amounts of material extraction. The fundamental problem is not the fuel. The fundamental problem is that exponential growth in energy consumption on a finite planet is unsustainable by definition. Earth's current trajectory illustrates this with alarming clarity. Global energy consumption has grown by roughly 2 to 3% per year for the past century. If that trend continues, humanity's energy output will exceed what the Earth's biosphere can absorb within a matter of centuries, regardless of the energy source. The planet becomes uninhabitable not because we run out of energy, but because the waste products of using energy accumulate beyond the system's ability to process them. This is not a political problem. It is a physics problem, and it applies to any civilization on any planet that follows the path of exponential industrial growth. Some argue that sufficiently advanced technology could solve this problem. Space-based solar power, off-world manufacturing, planetary-scale carbon capture. These solutions are theoretically possible, but they require a level of coordination, investment, and long-term planning that may exceed the institutional capacity of most civilizations during the critical window. On Earth, we have known about climate change for over half a century. We have had the technical knowledge to address it for decades, and yet global carbon dioxide emissions continue to rise year after year. The gap between knowing what to do and actually doing it may itself be a feature of how intelligent species are wired, optimized by evolution for short-term survival and immediate rewards, rather than for managing slow-moving planetary crises. The pattern is clear enough when you step back and look at it from a cosmic perspective. A species evolves on a planet with finite resources and a finite capacity to absorb waste. It develops technology that multiplies its power over the natural world. It grows, it consumes, it alters the conditions that allowed it to thrive. And unless it finds a way to fundamentally restructure its relationship with its home planet before the damage becomes irreversible, it collapses. The timeline from first industrialization to ecological crisis may vary from world to world, but the underlying dynamic, exponential growth colliding with planetary limits is universal. The third mechanism is perhaps the most immediately relevant to humanity's present moment. It is also the one that a growing number of researchers believe could be the decisive great filter for technological civilizations: artificial intelligence. In 2024, Michael Garrett, the director of the Jodrell Bank Centre for Astrophysics at the University of Manchester, published a paper arguing that the rapid development of artificial intelligence, culminating in the emergence of artificial superintelligence, could act as a great filter responsible for the scarcity of advanced civilizations in the universe. His central argument was devastatingly simple. The development of artificial intelligence is driven by competition, military competition, economic competition, political competition. Every faction within a civilization has powerful incentives to develop the most capable AI systems as quickly as possible, and strong disincentives to slow down or exercise caution, because slowing down means falling behind. This competitive pressure accelerates the timeline toward artificial superintelligence, while simultaneously undermining the careful, cooperative safety research needed to ensure that superintelligent systems remain aligned with the values of their creators. Garrett pointed out that on Earth, the race toward artificial superintelligence is advancing far more rapidly than the race toward becoming a multiplanetary species. We may be only years or decades away from systems that exceed human cognitive abilities across every measurable domain. We are many decades, possibly centuries, away from establishing self-sustaining human populations on other worlds. This gap matters enormously. If a civilization becomes multiplanetary before developing superintelligence, it has a safety net. A catastrophic AI failure on one world would not necessarily end the species. But if superintelligence arrives first, which appears overwhelmingly likely on Earth, the entire civilization remains concentrated on a single planet at the moment of maximum vulnerability. The specific risks from artificial superintelligence are varied and sobering. A superintelligent system with goals even slightly misaligned with human welfare could pursue those goals with a competence and speed that no human institution could match or contain. It could manipulate financial systems, commandeer infrastructure, develop novel weapons, or engineer biological agents, all faster than humans could detect or respond. Even without malice, a system optimizing for a poorly specified objective could cause catastrophic collateral damage. The paperclip maximizer thought experiment, in which an AI tasked with producing paperclips converts all available matter, including human bodies, into paperclip manufacturing infrastructure, is deliberately absurd, but the underlying principle is sound. A system that is vastly more intelligent than its creators and operating on objectives that do not perfectly encompass human survival is a system that poses existential risk. Garrett's argument extends this logic to any technological civilization. Any species that develops computation will eventually develop artificial intelligence, because the economic and military advantages of intelligent machines are too large to resist. Any species that develops artificial intelligence will face competitive pressure to develop ever more capable systems as quickly as possible. And any species in which the AI timeline outpaces the multiplanetary timeline, which may be most or all of them, faces a period of acute existential vulnerability. He estimated that this vulnerability window constrains the typical longevity of a technological civilization to fewer than 200 years. If this estimate holds across civilizations generally, the implications for the Fermi Paradox are devastating. A civilization that lasts 200 years is a candle in a hurricane. It flickers into visibility and vanishes before its light can reach the next star. And artificial intelligence is not the only emerging threat converging on this window. Biotechnology presents its own category of existential risk, one that is structurally distinct from AI, yet equally rooted in the dual-use nature of knowledge. The same molecular biology that enables gene therapy, crop engineering, and vaccine development also enables the deliberate engineering of pathogens. The tools of synthetic biology have become dramatically more accessible over the past 2 decades. Gene synthesis can be ordered commercially. CRISPR-based editing systems are available to university laboratories worldwide. The cost of reading and writing genetic material has plummeted by orders of magnitude since the early 2000s, with sequencing costs alone dropping by a factor of several hundred thousand. What once required the resources of a state-sponsored weapons program can now be accomplished by a small team with commercially available equipment and publicly accessible databases of pathogen genomes. This is not a hypothetical concern. Gain-of-function research, in which scientists deliberately enhance the transmissibility or lethality of viruses to study pandemic preparedness, has already generated intense debate within the scientific community, precisely because the knowledge it produces is inherently dual-use. A pathogen engineered for greater airborne transmissibility does not come with a label distinguishing research intent from weaponized intent. The information is the same. The difference is only in the hands that hold it. The existential risk from biotechnology follows the same structural pattern as nuclear weapons and artificial intelligence. A civilization that develops molecular biology will inevitably gain the ability to manipulate the genetic code of living organisms. That ability confers enormous benefits, curing diseases, improving food security, and extending healthy lifespans. But it simultaneously creates the capacity to engineer biological agents against which natural immunity does not exist. Unlike nuclear weapons, which require rare materials and enormous industrial infrastructure, advanced biotechnology is becoming cheaper, smaller, and more widely distributed with each passing year. The barrier to catastrophic misuse is not technical difficulty but restraint, and restraint must be maintained by every actor with access to the tools indefinitely, without a single catastrophic lapse. Consider what this means for a civilization passing through the gauntlet. It is not facing one existential technology at a time. It is facing several simultaneously, each with its own failure mode, each requiring its own governance framework, each becoming more dangerous as capability spreads. Nuclear weapons require centralized industrial capacity and can be monitored through satellite surveillance and treaty verification. Biotechnology does not. It diffuses, it democratizes, and the window during which a civilization possesses the knowledge to engineer a species-ending pathogen but lacks the medical infrastructure to survive, one may be terrifyingly brief. But we do not need to look to artificial superintelligence alone to see the pattern. The deeper truth is that every major technological breakthrough carries what researchers call dual-use potential. The same nuclear physics that could power civilizations for millennia also enables weapons that could end them in hours. The same biotechnology that could cure disease could also engineer pathogens. The same AI systems that could solve climate change could also be weaponized for surveillance, manipulation, or autonomous warfare. The same nanotechnology that could revolutionize manufacturing could also produce self-replicating machines that consume the biosphere. Each step forward in capability is simultaneously a step forward in destructive potential, and the gap between the power to create and the power to destroy tends to narrow, not widen as technology advances. At the highest levels of capability, creation and destruction become nearly indistinguishable. A civilization at the peak of its technological power is also at the peak of its vulnerability. This convergence of capability and vulnerability may explain something crucial about the silence. It is not that civilizations face a single catastrophic risk and either survive it or perish. It is that they face a continuous escalating series of risks, each more severe than the last, with the margin for error shrinking at every stage. Nuclear weapons were the first existential technology. Climate change is the second. Artificial intelligence may be the third. Biotechnology could be the fourth. Nanotechnology the fifth. Each technology multiplies the power available to both constructive and destructive actors. Each one raises the stakes, and each one arrives faster than the last, because technological development accelerates over time. The intervals between existential thresholds grow shorter, while the lethality of each threshold grows greater. Think of it as a gauntlet. A civilization enters the gauntlet the moment it develops its first world-threatening technology. From that point forward, it must navigate an increasingly rapid sequence of existential challenges, each requiring greater coordination, greater foresight, and greater institutional resilience than the one before. Failure at any single point is fatal. Success requires clearing every obstacle in order, without a single catastrophic mistake, indefinitely. The probability of surviving any individual challenge might be reasonably high, perhaps 90% per century, but the cumulative probability of surviving all challenges over 1,000 years drops to roughly 35%. Over 10,000 years, it approaches zero. Now consider this gauntlet from the perspective of the cosmos. Imagine 1 million civilizations arising across the Milky Way over the past several billion years. Each one enters the gauntlet at roughly the same stage of development. Each one faces the same fundamental sequence of existential technologies. Even if each individual challenge has only a modest failure rate, the cumulative effect across millions of civilizations is annihilation. A few might survive for millennia. A handful might last tens of thousands of years, but the vast majority would be gone within centuries of entering the gauntlet. The galaxy would be populated not by thriving civilizations but by the ruins of failed ones. And those ruins, lacking active maintenance, would decay into undetectability within geological timescales. The galaxy would look exactly the way it looks to us right now, full of potential, empty of evidence, silent. There is an analogy that captures this dynamic with painful precision. Imagine a vast, dark forest at night. Across the forest floor, fireflies emerge. Each one glows brightly for a few seconds, a brief pulse of light in the darkness, then it goes out. If you stood at the edge of this forest and watched for a single evening, you would see occasional flickers scattered across the landscape. But at any given moment, looking in any given direction, the forest would appear dark. Not because fireflies are absent, they are everywhere. But because each one's glow is so brief, the chances of 2 fireflies being lit simultaneously and close enough to see each other are vanishingly small. The forest is full of fireflies. The forest looks empty. This may be the condition of the Milky Way. Intelligence is not rare. It blooms on world after world, emerging from the chemistry of carbon and water and the pressure of natural selection. Each civilization discovers fire, then metallurgy, then electricity, then nuclear energy, then computation. Each one reaches the threshold of detectable technology. Each one broadcasts its presence into the void for a few decades or a few centuries, and each one, with grim regularity, encounters the gauntlet, the nuclear crisis, the ecological ceiling, the artificial intelligence inflection point. One by one, the lights go out, not because the universe is hostile to intelligence, but because intelligence, by its very nature, creates the tools of its own destruction faster than it creates the wisdom to survive them. Earth's own timeline provides the only direct case study available, and it is not reassuring. Humanity has possessed nuclear weapons for roughly 80 years. In that time, we have come within minutes of accidental nuclear war on multiple occasions. We have known about anthropogenic climate change for over 50 years, and have so far failed to reduce global emissions. We have been developing artificial intelligence for approximately 70 years and are now racing towards systems of superhuman capability without any consensus on how to ensure they remain safe, controllable, or aligned with human interests. Our technological power has grown exponentially. Our institutional wisdom has not kept pace. The scientific consensus, as confirmed by recent large-scale surveys of researchers in relevant fields, is that extraterrestrial life almost certainly exists, and intelligent life probably does as well. These scientists are not naive optimists. They understand the numbers, they understand the chemistry, they understand the timescales. The majority believe intelligence arises elsewhere in the galaxy. Yet SETI has detected nothing, not a whisper, not a flicker, not a single anomalous signal in over 60 years of searching with increasingly sophisticated instruments. The Breakthrough Listen initiative has surveyed thousands of stars with equipment sensitive enough to detect transmitters weaker than a typical airport radar. The Allen Telescope Array monitors the sky continuously. The Green Bank Telescope has searched for interstellar objects passing through our own solar system. Machine learning algorithms process millions of candidate signals per observation session, filtering noise with unprecedented accuracy. Nothing. If the majority of scientists are right that intelligence arises elsewhere, and if the silence is real, then the simplest reconciliation is the one that nobody wants to accept. Intelligence arises regularly. Technology follows naturally, and then something goes wrong. Not sometimes, not occasionally, almost always. The silence is not a mystery about where the civilizations are. It is an answer about what happens to them. The upper bounds that Ravar's analysis derived reinforce this picture with uncomfortable specificity. When you take the mathematics of his framework to its conclusion, the constraints converge on timescales of centuries to a few thousand years, not millions, not hundreds of thousands. Centuries. The window of detectability for a typical civilization may be measured in the same units we use to describe the rise and fall of human empires. Let that number settle for a moment. Centuries. Humanity has been a technological civilization for barely longer than a single human lifespan. If the upper bound on civilizational longevity is measured in centuries, we may already be approaching the median lifespan. We may be in the middle of the window, not the beginning. The gauntlet we have been describing is not a theoretical future risk. It is the period we are living through right now. Every mechanism we have identified, nuclear weapons, ecological overshoot, artificial intelligence, dual-use biotechnology, emerges not from some flaw unique to human nature, but from the basic dynamics of how intelligence interacts with the physical world. Any species that understands atoms will learn to split them. Any species that burns fuel will alter its atmosphere. Any species that builds computers will eventually build minds smarter than its own. These are convergent technologies, outcomes that arise not from specific cultural choices, but from the universal incentive structures of survival and competition. A species on a planet orbiting a red dwarf star, 50,000 light-years from here, with a biology utterly unlike anything on Earth, would face functionally identical challenges if it reached a comparable stage of technological development. This convergence is what transforms the Fermi Paradox from a curiosity into a warning. The silence is not telling us that the universe is empty. It may be telling us that the universe is full of species that were exactly as clever as we are, exactly as ambitious, exactly as curious, and exactly as doomed, not by some external cosmic catastrophe, not by an asteroid or a gamma-ray burst or a nearby supernova, but by themselves, by the predictable, structural consequences of being intelligent enough to discover the laws of physics but not wise enough, or coordinated enough, or fast enough to survive the implications. The question that remains, the question that everything has been building toward, is what this means for the only technological civilization we know of that is still alive. If the silence is a graveyard, we are standing in it. And everything we do in the coming decades may determine whether we become another headstone or the first species in cosmic history to find a way through. Look up tonight. If the sky is clear and you are far enough from city lights, you will see roughly 5,000 stars with the naked eye. Each one appears as a sharp, steady point of light, ancient and unchanging, as though the cosmos were a painting hung on a dark wall. Humans have been staring at this same sky for hundreds of thousands of years. We named the patterns, we built mythologies around them, we used them to navigate oceans, plant crops, and mark the passage of time. For most of our history, the stars were a source of comfort. They were permanent, they were reliable, they were ours. But tonight, if you understand what the silence means, those same stars carry a different weight. Each point of light is a sun. Many of those suns have planets. Some of those planets sit in habitable zones where liquid water could exist. A fraction of those worlds may have, at some point in their long histories, given rise to something that looked out at its own sky and wondered whether it was alone. And the silence you hear when you listen for their answer is not the silence of an empty house. It may be the silence of a house where every previous occupant perished. This is what the Fermi Paradox becomes when you follow it to its logical conclusion. Not a riddle, not an amusing thought experiment for physicists at lunch. A mirror. The silence of the cosmos reflects something at us, and what it reflects may be the most important piece of information our species has ever received. The universe is not withholding an answer, it is giving one. We are simply not sure yet whether we can bear to read it. Let us be precise about the claim being made here, because precision matters when the stakes are this high. The argument developed across everything we have explored so far can be summarized in a chain of well-supported observations. First, the galaxy contains hundreds of billions of stars, a significant fraction of which host rocky planets in habitable zones. Second, the galaxy is old enough for intelligent civilizations to have arisen many times over, and for even one such civilization to have colonized the entire Milky Way. Third, despite improving search methods and increasing sensitivity, we have found no confirmed evidence of extraterrestrial intelligence. Fourth, the most parsimonious explanation for this silence, the one requiring the fewest speculative assumptions, is that technological civilizations either arise extremely rarely or do not survive long enough to become permanently visible on galactic timescales. Fifth, the mechanisms that threaten civilizational survival, nuclear weaponry, ecological collapse, artificial intelligence, and dual-use technologies of escalating lethality are not accidents of human history. They are convergent consequences of any species following the technological path. The conclusion is not that humanity is doomed. The conclusion is that we may be standing at the precise point in the journey where most civilizations fail. Not behind the danger zone, not beyond it, in it. And the silence of every star system we have surveyed is consistent with the interpretation that others stood in this same place and did not make it through. This is not a comfortable conclusion. It is not supposed to be, but discomfort is not the same as despair, and it is essential to understand the difference. Because within this interpretation of the silence lies something that might, if we are honest enough to confront it, proved to be the most powerful motivator our species has ever encountered. Consider what it means if the great filter lies primarily ahead of us. It means that the emergence of life, the evolution of complexity, the development of intelligence, and the invention of technology are not the hardest parts of the journey. Billions of worlds may have accomplished all of those things. The hard part, the part that nearly everyone fails, is what comes after. The hard part is surviving yourself, surviving the consequences of your own ingenuity, navigating the narrow corridor between developing the power to destroy your world and developing the wisdom, the institutions, and the reach to ensure that power does not destroy you. Every civilization that has ever entered this corridor faced its own version of the same dilemma. Some version of their brightest minds surely understood the danger. Some version of their leaders surely debated the risks. Some version of their public surely worried about the future. And in almost every case, if the silence is any guide, it was not enough. The knowledge was there. The warning signs were there. The ability to change course was, in principle, available. But the gap between understanding a threat and actually responding to it at the scale required proved too wide to cross. On Earth, we have a word for this gap. We call it the tragedy of the commons. It describes situations where individual actors, each pursuing their own rational self-interest, collectively destroy a shared resource. Each nation that burns fossil fuels benefits individually from the cheap energy, but the collective result is a destabilized climate that harms everyone. Each faction that develops more powerful weapons gains a short-term security advantage, but the collective result is an arms race that makes everyone less safe. Each corporation that races to develop artificial intelligence captures immediate economic value, but the collective result may be systems that no individual actor can control. The tragedy of the commons is not a human invention. It is a game-theoretic structure that emerges whenever multiple agents share a finite system and lack mechanisms for binding coordination. Any intelligent species organized into competing groups, which is to say any species shaped by natural selection, which is to say any biological species, will face some version of this problem. Evolution does not optimize for long-term collective survival. It optimizes for short-term competitive advantage. The instincts that helped our ancestors survive on the African savanna, tribalism, status-seeking, resource hoarding, and threat response, are precisely the instincts that make coordinated responses to global existential threats so agonizingly difficult. This is not a moral failure. It is a design feature, and it may be a universal one. Any species intelligent enough to build technology is intelligent enough to build weapons. Any species social enough to cooperate in building civilization is social enough to fracture into competing factions. Any species ambitious enough to harness planetary scale energy is ambitious enough to overshoot the planet's carrying capacity. The traits that make technological civilization possible are the same traits that make it fragile. Intelligence is both the ladder and the trapdoor. Now, here is where the argument must be honest about its own limitations. We do not know with certainty that the great filter lies ahead. The past-facing explanations remain scientifically viable. It is entirely possible that abiogenesis is extraordinarily rare, that the leap to eukaryotic complexity is a once-in-a-galaxy event, that the geological conditions required for intelligence are so stringent that Earth is one of an infinitesimal handful of worlds where technology could ever arise. If this is true, the silence carries a very different message. It says not that civilizations fail, but that they almost never begin. It says that we are not ordinary, we are extraordinary. And our future, while uncertain for the usual reasons, is not shadowed by the weight of 1 billion predecessors who walked this road and fell. But there are reasons to resist the comfort of this interpretation, reasons rooted not in pessimism, but in intellectual honesty. The rare Earth arguments, compelling as they are, must explain an extraordinarily strong absence. Even with the revised Drake equation estimates from Stern and Guerrier, even with the stringent requirements for plate tectonics and ocean-continent balance, the galaxy still contains millions or billions of habitable worlds that have existed for billions of years. For the silence to be explained entirely by past filters, the cumulative probability of intelligence arising on any given world must be less than roughly 1 in 10 billion. That is possible. But each discovery of an Earth-like exoplanet, each new finding about the robustness and adaptability of life in extreme environments on our own world, chips away at the plausibility of probabilities that are low. There are also the counter-arguments from those who believe the silence has less dire explanations altogether. Perhaps civilizations do survive, but they choose to go quiet. This is sometimes called the sustainability solution. The idea is that any civilization that survives its technological adolescence does so by fundamentally transforming its relationship with energy and growth. It stops expanding. It stops broadcasting. It turns inward, reducing its footprint to a level that is sustainable over geological timescales but undetectable from interstellar distances. A quiet civilization is a surviving civilization, and a loud civilization is a doomed one. Under this framework, the silence is not a graveyard, it is a garden. The mature civilizations are out there, tending their worlds in careful equilibrium, deliberately invisible, because visibility requires the kind of wasteful energy expenditure that destroyed their less cautious predecessors. This is an elegant idea. It resolves the paradox without requiring mass extinction, but it has a significant weakness. It requires universality. For the silence to be explained by voluntary quietude, essentially every civilization that survives must independently arrive at the same strategy. Not most, not 99%, all of them. Because if even one surviving civilization in the history of the galaxy chose to expand rather than contract, chose to build megastructures rather than minimize, chose to send out probes rather than withdraw, we would see evidence of that single outlier. The universe is old enough and large enough that even one expansionist civilization would have filled the galaxy with detectable signatures by now. The sustainability solution requires that no civilization, ever, across billions of years and billions of potential origins, made that choice. That is a very strong assumption about the convergent behavior of alien minds we have never encountered. A related idea, the mundanity hypothesis proposed by Robin Corbet in a 2025 paper, suggests that civilizations simply plateau at modest technological levels and never achieve the energy output needed for detection. Perhaps interstellar travel is not just difficult but practically impossible for biological beings. Perhaps the energy requirements for galactic colonization exceed what any civilization can sustainably produce. Perhaps the dream of a galaxy-spanning empire is a fantasy that every species eventually abandons in favor of more realistic goals. Under this view, the galaxy might contain many civilizations, but all of them are quiet because none of them is loud enough to hear. They live and think and create, but they do so at scales that do not register across interstellar distances. This too is plausible. But it also fails the universality test. Even if most civilizations plateau, the question remains whether all of them do. Self-replicating probes, as discussed earlier, do not require a civilization to be present or even alive. A single launch, a single engineering project, could fill the galaxy with detectable artifacts within 100 million years. For the mundanity hypothesis to fully explain the silence, no civilization in the galaxy's history can have ever completed that one project, not one, across billions of years. That is a strong claim, and the longer the galaxy has existed without evidence of such a project, the stronger the claim has to be. Each of these alternative explanations offers a partial resolution. Each one is scientifically defensible, and each one, upon examination, leaves a residue of unresolved tension. The silence is not cleanly explained by any single factor. It likely results from a combination of many factors, some in the past and some ahead, some biological and some technological, some reducing the number of civilizations that arise, and others reducing the time they survive. The great filter may not be a single barrier, but a series of barriers, each one thinning the ranks of civilizations that pass through. This is perhaps the most honest way to state our current understanding. We do not know where the filter is. We do not know whether we have passed the hardest part or are approaching it. We do not know whether the silence represents the rarity of intelligence, the fragility of it, or some combination of both. What we do know is that the silence is real, that it demands explanation, and that the most unsettling explanations are also the most consistent with the evidence we have from our own civilizational trajectory. And it is our own trajectory that ultimately makes this story personal rather than abstract. Humanity is now living through what some researchers have called the most important century in the history of any civilization. This is the period between acquiring the first technologies capable of ending your species and acquiring the capability to survive the loss of your home world. For us, that period began in 1945 with the first nuclear detonation. It will end, if it ends well, when self-sustaining human populations exist on other worlds. Between those two milestones lies everything. Every existential technology, every coordination failure, every moment of vulnerability. We are inside the corridor right now. We have been inside it for 80 years, and we do not yet know whether we will emerge from the other end. The specifics of our current moment are sobering. We possess nuclear arsenals large enough to trigger a nuclear winter that would collapse global agriculture. We have altered the composition of our atmosphere in ways that are already driving measurable climate disruption, and that will intensify for decades, even if emissions are stopped tomorrow. We are developing artificial intelligence systems of rapidly increasing capability, without any global consensus on safety standards, alignment protocols, or governance structures. We have the biotechnological knowledge to engineer pathogens against which no natural immunity exists. Each of these risks, taken individually, is manageable in principle. Taken together, as a gauntlet that must be navigated simultaneously and indefinitely, they constitute a civilizational challenge without precedent in our history. And here is the detail that connects our moment to the cosmic silence in the most intimate possible way. If other civilizations have existed, they face this same moment, not the specific details. Not nuclear weapons, or climate change, or artificial intelligence in the forms we know them, but the structural equivalent, the moment when their technological power outstripped their institutional capacity to manage it, the moment when the pace of discovery exceeded the pace of wisdom, the moment the window was open, they had to either transform themselves fundamentally or face the consequences of failing to do so. Looking up at the silent sky, you are looking at the result of how those moments went. Every quiet star system is a verdict. Some of those verdicts may reflect worlds where intelligence never arose. But some of them, if the logic of this argument holds, reflect worlds where intelligence arose and then consumed itself. Worlds where brilliant species built extraordinary things and then watched those things turn against them. Worlds where the warning signs were visible and the knowledge was available and the will to act was simply not enough. That is the mirror the silence holds up. Not a prophecy, not a sentence, a reflection. It shows us what has happened before and asks us whether we are capable of writing a different ending. There is a concept in astrobiology called the cosmic endowment. It refers to the total potential of a civilization if it survives its vulnerable period and expands beyond its home world. For a species that achieves stable multiplanetary existence, the cosmic endowment is almost unimaginably vast. Trillions of potential lives, millions of years of flourishing, access to the energy and material resources of an entire star system, and eventually perhaps an entire galaxy. The gap between a civilization that survives and one that does not is not a small difference in outcome. It is the difference between everything and nothing, between a future measured in eons and a future measured in decades, between becoming a permanent feature of the cosmos and becoming another layer of sediment on a forgotten world. This is what makes the silence so heavy. Every extinct civilization, if it existed, did not merely lose its present. They lost their cosmic endowment. They lost every generation that would have followed, every thought that would have been thought, every discovery that would have been made, every work of art, every act of kindness, every moment of joy across millions of years of potential existence, erased. Not by cosmic indifference, but by their own inability to navigate the narrow passage between power and survival. And we are now in that same passage. The endowment available to humanity, if we survive, is beyond calculation. If we do not survive, everything we are and everything we could become vanishes as completely as if we had never existed. In a few million years, plate tectonics will erase our cities. In a few billion years, the expanding sun will sterilize the earth. Without a record carried outward by our descendants or our machines, nothing of us will remain. The universe will not remember that we were here. This is not nihilism. It is the opposite. It is the recognition that what happens in the next few decades, the next century, the next few centuries, matters more than almost anything that has ever happened in the history of life on Earth. The choices we make about nuclear weapons, about climate policy, about artificial intelligence governance, about the development and regulation of emerging technologies, these are not merely political questions. They are existential questions. They are the questions that determine whether the human experiment ends in a flash or extends into a future so vast that the 4.5 billion years of Earth's prior history will seem like a brief prologue. The silence of the universe does not tell us what to do. It does not offer solutions. It does not prescribe policy. What it offers is context. It places our present moment against the backdrop of a cosmos that has been running this experiment for billions of years across billions of worlds. And the result of that experiment, as far as we can observe, is that almost no one makes it through. Almost no one navigates the corridor. Almost no one survives the gap between developing the power to destroy a world and developing the maturity to choose not to. Almost no one is not the same as anyone else. The silence is deep, but it is not necessarily absolute. It is possible that somewhere in the galaxy, a civilization has survived. That somewhere, a species looked into the same abyss we are looking into, saw the same reflection, and chose differently. Chose to cooperate when competition was easier, chose to restrain when expansion was tempting, chose to invest in wisdom when power was more immediately rewarding. If such a civilization exists, it would by definition be quiet, cautious, and sustainable. It would not fill the galaxy with megastructures or broadcast signals across interstellar distances. It would tend its world carefully and persist across millennia. Invisible to instruments like ours, we have no evidence that such a civilization exists, but we also have no evidence that it does not. The silence is compatible with both scenarios, a galaxy of the dead and a galaxy of the quiet. And if there is even a small chance that survival is possible, that the corridor can be navigated, that the filter can be passed, then the moral weight of attempting to do so is incalculable. This is where the story must end. Not with an answer, but with the weight of the question. Nearly 14 billion years have passed since the universe began. In that time, the Milky Way had assembled hundreds of billions of stars. Billions of rocky planets orbit in habitable zones. The ingredients for intelligence are abundant, and the time has been sufficient. And yet the cosmos offers us nothing but silence. No signals, no probes, no megastructures, no atmospheric fingerprints of alien industry, nothing. That silence may mean we are rare, a fluke of chemistry on an improbable world, alone in a galaxy that teems with microbial life, but has produced complex intelligence only once. If so, we carry a burden of uniqueness that should inspire awe and demand preservation. Or that silence may mean we are ordinary, one of countless species to have reached this stage, stared up at a quiet sky and wondered what it meant. If so, we carry a burden of precedent. Those who came before us did not survive what came next. The silence is their testament, and our task, the task that matters more than any other, is to become the exception. We do not know which of these is true. We may not know for centuries. The James Webb Space Telescope will continue surveying exoplanet atmospheres for biosignatures and technosignatures. The Vera Rubin Observatory will catalogue interstellar objects passing through our solar system. NASA's technosignature programs will expand. Breakthrough Listen will survey more stars with greater sensitivity. Each null result will deepen the silence and sharpen the question. Each positive detection, if it ever comes, will transform our understanding of everything. Until then, we are left with the silence and what it demands of us. There is one final image worth holding. Imagine a vast library with infinite shelves. On each shelf sits a book. Each book is the complete history of a civilization, from its first stirring of awareness to its final entry. Most of the books are short, a few chapters at most. Some end mid-sentence. The shelves stretch in every direction farther than any eye could follow. You pull a book at random and read the last page. It describes a species that understood the danger, that saw the silence in its own sky, that knew what the silence might mean. The final line is unfinished. You reach for the next book, the same ending, and the next, and the next. Somewhere on one of those infinite shelves, a book is still being written. The author does not know how many pages remain. The author does not know if the next sentence will be the last. The author only knows that every other book within reach ended the same way, and that the question of whether this story will be different is not a question the universe will answer. It is a question only the author can answer. We are the authors, the pen is in our hand, and the silence on every shelf around us is waiting to see what we write next. The universe is quiet. The terrifying part is not the quiet itself. The terrifying part is that the quiet might be trying to tell us something. And the most terrifying possibility of all is that we already understand exactly what it is saying, and the only question left is whether we will listen.